Our universe started with the Big Bang, but only for the right definition of our universe, and started for that matter. In fact, the Big Bang is probably nothing like what you were taught. A 100 years ago, we discovered the beginning of the universe. Observations of the retreating galaxies by Edwin Hubble and Vesto Slipher, combined with Einstein's then brand new general theory of relativity, revealed that our universe is expanding. And if we reverse that expansion far enough, mathematically, purely according to Einstein's equations, it seems inevitable that all space and mass and energy should once have been compacted into an infinitesimally small point, a singularity. It's often said that the universe started with this singularity, and the Big Bang is thought of as the explosive expansion that followed. And before the Big Bang singularity? Well, they say that there was no before because time and space simply didn't exist. Now, if you think you've managed to get your head around this bizarre notion, then I have some bad news. That picture is wrong, at least according to pretty much every serious physicist who studies the subject. The good news is that the truth is way cooler, at least as far as we understand it. Now, before a certain crowd starts with all the scientists keep changing their minds, they don't know anything, or the Big Bang Theory is just a theory, let me be very clear. The evidence for a hot, dense early universe is practically incontrovertible. The cosmic microwave background is a direct line of sight to the universe as it was only a few 100,000 years after the hypothetical beginning of time. We can see pretty much directly that all space and matter in the universe was once crunched at least 1,000 times closer together. There's also the relative abundance of simple elements, hydrogen and helium in particular, whose ratio is exactly what we expect if the entire universe was a dense, billions of degrees nuclear furnace for the first several minutes of its existence. In fact, there's powerful evidence that we should not rewind Einstein's equations that far, at least without introducing some very new physics. For one thing, there's also convincing observational evidence that the time before around 10 to the power of -32 seconds included a period of extremely rapid expansion called cosmic inflation. We've talked about the reasons we need inflation in previous episodes, and I'll come back to it in a bit. Adding that initial growth spurt solves a couple of the big problems with the Big Bang Theory, but it doesn't change the fact that rewinding the expansion of the universe, even at different speeds, still leads us towards the t=0 singularity. I'm going to come back to why we need to forget the idea of this singularity. Doing so will change the way we think about cosmic inflation and about the beginning of the universe. But before we kill the whole idea of the Big Bang singularity, we need to understand what we're killing. What does it really mean for all of space to be compacted into a single point? This idea is especially weird if the universe is infinite. Now, the universe may or may not be infinite, but if we can understand this for the infinite case, then getting all of this for the finite case is baby stuff, at least by comparison. It's tricky to talk about the size of an infinite universe. Instead of the overall volume or radius, we talk about the size of an expanding infinite universe in terms of the scale factor. That's the distance between any two points in space at some moment in time relative to their distance at some other reference moment. That reference moment is typically taken to be right now, so the scale factor of the universe is currently 1. Several billion years ago, the scale factor was half. All points in the universe were half as far apart as they are today. So when I talk about rewinding the expansion, I mean running the clock backwards to track the shrinking scale factor. One way to do that is to keep halving the scale factor. Do that enough times and any two points, no matter how far apart they were, will end up as close together as you'd like. Do it enough times and the universe could end up as hot and dense as you like. But it'll still be infinite, spatially. The scale factor is incredibly small, but an incredibly small number times infinity is still infinity. Rewinding the universe this way doesn't leave us with a singularity. The singularity is when all points are not just next to each other, but literally in the same spot, at which point temperature and density are infinite. That last tiny step is a doozy. The scale factor goes from incredibly small to 0. So the infinite universe becomes infinitesimal. All points become the same point, and three-dimensional space becomes zero-dimensional. That's the singularity. We say that it didn't happen in any one place because a point is zero-dimensional. There weren't spatial dimensions for it to happen in. At the same time, we say the Big Bang happened everywhere at once because even the tiniest fraction of a second later, the universe has infinite size and everywhere is expanding equally. Even if the universe is not infinite, then whatever space there is comes into being at the same time from that singularity. But what happens to time at the Big Bang singularity? To get that, you can't think about the universe as having one big clock that rewinds and then winks out of existence at the Big Bang, or into existence if you're going forward. No, you have to think about time in the way Einstein intended. There is no universal clock. Time is relative. Clocks are attached to each observer, each moving frame of reference. To see what time does at the Big Bang, we have to trace a path through space and time back to the singularity. We trace a path called a geodesic, which in general relativity is the shortest path between two space-time coordinates. These are the grids we use to map space-time. Remember that in our rewind, all points in the universe get arbitrarily close together before merging at t equals 0. Well, that's the same as saying that all geodesics in the universe converge at the Big Bang singularity. In the same way, all lines of longitude converge at the North Pole. So, each geodesic tracks earlier and earlier times as it approaches the Big Bang, infinite clocks rewinding towards 0. And then they all converge. And then what? Well, then nothing. All geodesics end at the Big Bang singularity, and their timelines end with them. Or they start, depending on how you want to think about it. The point is that in the pure Einsteinian picture, there is no before the Big Bang, because no timeline in this universe can be traced there. This is called geodesic incompleteness, and it also happens at the singularity in the center of a black hole. All timelines end, this time in the forward direction. The analogy with the North Pole is a good one, and Einstein himself used it. Lines of longitude end at the North Pole, and it's meaningless to ask what is north of the North Pole. From the pure Einsteinian point of view, it's meaningless to ask what happened before the Big Bang or after reaching the black hole's center. Okay, so I'm taking my time to explain something I already told you is wrong. But it's important because the extreme weirdness of the Big Bang singularity is part of what tells us it's wrong. Anytime you encounter a singularity in the mathematics of a physical theory, you have good reason for skepticism. It's probably telling you that your physical theory is incomplete and that you pushed that theory too far. That's what's happening here. We used general relativity to rewind the universe. But we already know that despite its incredible successes, GR is an incomplete theory. At the crazy densities and temperatures of the Big Bang singularity, and just after, GR comes into terrible conflict with quantum mechanics. Now, we've talked about that conflict and its possible resolutions before, but the upshot is that we just don't know how the universe behaves in those conditions. But we do know that pure general relativity is not a good description, and so we probably shouldn't believe its prediction that all space was compacted into a single point and that this is where time started. Okay, so what are the alternatives? Can we really track geodesics and the timelines they embody through the Big Bang and out the other side? If so, what do we find there? There are several possibilities, and they deserve their own episodes, and we'll actually get to those soon. But to whet your appetite. First up, cosmic inflation can offer a temporary reprieve from the singularity. Eternal inflation suggests that our universe appeared as a regularly expanding bubble in an unimaginably larger continuously inflating spacetime. In that case, before the Big Bang was a period of exponential expansion that could have lasted indefinitely. We'll get to the nitty-gritty of that with its inflatons and bubble universes real soon. There are also various cyclic universe options. The first cyclic universe idea was the Big Bounce, in which the gravitational attraction of all matter in the universe was enough to cause it to recollapse and then presumably bounce outward again. We now know that there isn't anywhere near enough matter to do that. Unless we bring in string theory. The Steinhardt-Turok model suggests that our universe floats in a higher dimensional space, living on geometric objects called branes. Collisions between those branes initiate cycles of expansion and contraction. Then there's Roger Penrose's conformal cyclic cosmology. It's even weirder because it postulates the infinite future boundary of an eternally expanding universe looks like the Big Bang of a new universe mathematically. So our heat death is someone else's Big Bang. There are some less abstract ways to get a new universe out of an old one. For example, an extreme quantum fluctuation could initiate a new Big Bang given infinite time. Or the same amount of time could lead to all particles randomly converging back to the same spot. Or maybe black holes birth new universes, as in Lee Smolin's fecund universe hypothesis. There's a poetry to that last one. The geodesics approaching the black hole singularity become the geodesics emerging from the new Big Bang singularity. People love cyclic and regenerating universes. They appeal to our sense of narrative, which might be a reason to be wary of these hypotheses. Now, they also appeal to our intuition for causality. Things happen because prior events caused them. Many of our ideas just push back the uncomfortable something from nothing moment. Physicists have a thing or two to say about that, from quantum fluctuations from nothing to Stephen Hawking's timeless interpretation of internal inflation that draws on the holographic principle. All things we'll discuss in the future as we travel beyond the beginning of spacetime.